It's almost like science fiction. The idea that one day doctors could listen to your heartbeat and even hear your thoughts without needing to touch you. But what if this technology was not just a fantasy but a reality? Scientists at Rice University have made an astounding breakthrough in medical diagnostics and brain research. They have created a revolutionary technology that uses quantum vibrations, so sensitive they can detect biological activity through solid walls. Yes, you heard that right, through solid walls. They can detect the subtle patterns of thought inside the human brain. This remarkable breakthrough, which leverages the strange but powerful principles of quantum physics, could someday allow doctors to listen in on the body without touching it, providing real-time insights into health, disease, and perhaps even the mysterious workings of the human mind. Join us as we delve into the world of quantum mechanics and explore how Rice University scientists have developed a quantum stethoscope that can literally listen to the heartbeat of the universe and decipher the language of our thoughts. At the heart of this discovery is the manipulation of phonons, tiny quantum-level vibrations that travel through materials much like ripples, moving across the surface of water. For decades, scientists have studied phonons and how they can be used to understand the properties of various substances. But Rice University's team has found a way to make these vibrations interact and interfere with each other far more strongly than anyone thought possible. And this is achieved by creating a unique three-layer quantum sandwich composed of ultra-thin sheets of silver, graphene, and silicon carbide. They amplify these effects to a record-breaking degree. The result is a device so sensitive that it can pick up the faintest biological signals, including a beating heart, active neurons firing in the brain, and even the subtle metabolic activity of individual cells. Imagine standing on the other side of a wall and not only sensing someone's pulse, but also being able to analyze their brain activity in real time. This is no longer the stuff of science fiction. The Rice researchers' innovation effectively turns phonons into a quantum stethoscope, a tool that could redefine what non-invasive medical imaging means. You might be wondering, what are phonons? Well, phonons are quantizations of vibrational energy, similar to how light waves are quantizations of electromagnetic energy. Just as photons are the smallest possible packet of light, phonons are the smallest possible unit of vibrational energy. When atoms in a material vibrate, they do so at specific resonant frequencies. These vibrations can be thought of as a wave traveling through the material, like ripples spreading across the surface of a pond. Photons were first proposed by Soviet physicist Yakov Frenkel in 1932 and have been studied extensively in condensed matter physics since then. They play a crucial role in understanding the thermal and electrical properties of materials. To put it simply, phonons are vibrations at the atomic level that carry energy through solids. They are all around us and are responsible for many of the physical phenomena we experience in our daily lives, such as heat conduction and sound propagation. In fact, the word phonon comes from the Greek word phone, which means sound. And indeed, sound waves are a familiar example of vibrations that travel through a medium. In this case, the air molecules around us. But phonons are not limited to the range of frequencies we can hear. They encompass a much broader spectrum, including the higher frequencies that our ears cannot detect. Traditionally, medical imaging technologies such as magnetic resonance imaging (MRI), positron emission tomography (PET scans), or ultrasounds rely on more conventional forms of energy to visualize the internal structures and activities of the body. MRI machines, for instance, use strong magnetic fields and radio waves to generate detailed images of organs and tissues. PET scanners detect gamma rays emitted by radioactive tracers injected into the body to show metabolically active areas. Ultrasounds employ high-frequency sound waves that bounce off internal structures to create real-time moving images. Each of these techniques provides valuable insights into the body, but they have limitations. MRI can be expensive, time-consuming, and may not be suitable for patients with certain metal implants or claustrophobia. PET scans involve ionizing radiation, which raises concerns about potential harm to healthy tissue. And ultrasounds, while generally safe, require trained operators and specialized equipment. Rice University's breakthrough lies in leveraging the power of quantum mechanics to offer an alternative approach. Their quantum stethoscope operates on the principle that every object, including the human body, is constantly emitting and vibrating at different frequencies. These vibrations, known as phonons, correspond to different types of energy, such as heat or mechanical motion. The innovation involves creating a device that can detect these incredibly faint vibrations at a distance without physical contact. The team achieved this feat by engineering a unique material structure that acts as an amplifier, boosting the signals from the body to levels that can be measured accurately. One of the key components of this invention is graphene, a two-dimensional material renowned for its exceptional electrical and mechanical properties. Graphene's atomic thickness and unique bonding structure make it an ideal candidate for amplifying and manipulating phonon vibrations. By incorporating graphene into their device, the researchers were able to enhance the sensitivity to the point where they could detect minute changes in frequency corresponding to biological activity. Imagine a scenario where instead of waiting for symptoms to appear and diseases to progress, doctors could continuously monitor patients in real time, spotting potential problems at their earliest stages when interventions are most effective. This could mean catching a heart condition like atrial fibrillation, diagnosing early signs of Alzheimer's disease, or monitoring the recovery process after a stroke or surgery. Moreover, the potential applications extend beyond traditional medicine. Security personnel, for example, might use the technology to identify individuals concealed behind barriers, or structural engineers could monitor the integrity of buildings and bridges by sensing vibrations through solid surfaces. Dr. Edwin Thomas, a materials scientist working on the project, emphasizes the paradigm shift this technology represents. For the first time, he states, we can use phonons not just as a theoretical concept, but as a practical tool for understanding the most delicate biological processes without physically touching the system we ray observing. The implications are extraordinary. So how exactly does this quantum stethoscope work? The device consists of a thin layer of silver sandwiched between two layers of graphene and silicon carbide. Silicon carbide, known for its hardness and high melting point, forms the bottom layer. Graphene, famed for its electrical conductivity and flexibility, sits in the middle. And finally, a thin layer of silver completes the structure. These layers are chosen not only for their unique properties, but also because they form an effective pathway for phonons to travel and interact. When placed near a biological source, such as a person, the device starts to vibrate at different frequencies depending on where the source is located. Importantly, it is not picking up sounds in the air, but rather vibrations directly through solid surfaces like skin or bone. These vibrations are then converted into an electrical signal for analysis. What's remarkable is the device's sensitivity. It can detect minute changes in frequency, variations in vibration caused by biological processes like a heartbeat or neural activity. These changes are so subtle they would be impossible to perceive with the human ear alone. The beauty of this innovation lies in its simplicity and effectiveness. It harnesses the power of quantum mechanics without requiring complex, expensive equipment. The device is relatively easy to fabricate using existing nanotechnology techniques, suggesting that mass production and wider accessibility may be feasible in the near future. However, there are challenges ahead. While the technology has shown great promise in laboratory settings, translating it into practical medical applications will require further research. Questions about data privacy, security, and the ethical implications of such sensitive technology need careful consideration. Moreover, integrating this invention into existing healthcare systems and workflows will require not only technological advancements, but also social and regulatory adaptations. One of the most fascinating aspects of this discovery is its potential to revolutionize the way we understand the brain. Neuroscientists have long sought to map brain activity to unravel the complexities of human thought, emotion, and behavior. Traditional methods such as electroencephalography (EEG) and magnetoencephalography (MEG) involve placing electrodes on the scalp or around the head to measure electrical and magnetic signals. While informative, these techniques have limitations in terms of spatial resolution and depth of penetration. The quantum stethoscope offers a unique opportunity to measure brain activity from a distance without physical contact, potentially providing a clearer, more comprehensive view of neural activity. Imagine a future where doctors could detect signs of neurological disorders like Alzheimer's or Parkinson's disease at their earliest stages, even before symptoms are apparent, or consider the potential to monitor the recovery of patients who have suffered brain injuries or strokes to guide rehabilitation efforts. Such applications are no longer science fiction. They are within reach of this revolutionary technology. As with any groundbreaking scientific advance, the discovery of the quantum stethoscope raises ethical questions that must be carefully considered. The ability to measure brain activity remotely without the need for invasive procedures opens up new frontiers in understanding the human mind. But with this power comes the responsibility to use it ethically and with respect for individual rights and privacy. Ensuring patient consent, data security, and responsible interpretation of highly sensitive information will be crucial. As this technology advances, despite the challenges, the potential benefits are too significant to ignore. This discovery marks a new chapter in our understanding of the body and mind. By harnessing the power of quantum mechanics, scientists have opened up a world of possibilities that were once confined to the realm of imagination. The future of medicine and neuroscience is bright, and this quantum stethoscope is leading the way. And that's all for today. Thank you for watching, and please don't forget to subscribe for more amazing content.